Good morning, friends. My name is Samita, and today's my lecture is on representation of floating point numbers, that is real numbers. So how we represent? The floating point format is similar to scientific form, where the real numbers consist of two parts. One is mantissa and other is exponent. Okay, for example, if we have 5.327 into 10 raised to power in scientific form will be 5.327, 10 raised to power 7 is E7 in the floating point format. Okay, we will represent E7 as a 10 raised to power 7. So the floating point number is said to be normalized or standard floating point number if magnitude of mantissa lies less than 1.0 and greater than 0.1. 0.1 से बड़ा होना चाहिए और 1.0 से less than होना चाहिए. So mantissa should be lie between 0.1 and 1.0. Should be less than equal to 0.1 and should be greater than 0.1 and should be less than 1.0. So the floating point number 0.00325 E minus 2. So you can write this number 5.327 into 10 e raised to power. So suppose you have a number 0.00325 e minus 2, you can be expressed as 0.325 e power minus 4. So keep the digit here and it increases e minus 4. So it is in the normalized floating point representation. So the real numbers are represented in computer memory as normalized binary floating point number. Okay, suppose floating point number is represented in 4 consecutive bytes, then out of these 4 bytes the mantissa is represented in the lower order 3 bytes and the exponent is in the most significant byte or such a standard format. So 32-bit is 8-bit biased exponent, 1-bit sign bit and 23-bit is the mantissa. Total is 32-bit format. So steps to represent the floating point number binary are as under. For example, convert decimal number to the binary equivalent and by using the decimal to binary conversion. First step is convert decimal number to the binary number. Then second is convert binary number to the normalized floating form. Okay. Then mantissa of binary normalized floating point number is extended to 23 bits. Okay, and by adding 0 to the right of it, by just adding 0 to the right of it so it is extended to 23 bits. Then fourth step, exponent of the binary floating point number is converted to biased exponent by adding 128 to the actual exponent. So fifth point, if the number is positive then sign bit is mantissa is 0 and for negative number the sign bit if mantissa is 1. Then last step, combine the sign bit, mantissa bit and biased exponent bit in binary format given below. So first is 8-bit biased exponent, 1-bit sign bit, 23-bit mantissa. Let's see one example. So for example, represent plus 12.5 minus 12.5 in 32-bit format floating point form. So what do you do first? 12.5 to the binary. So how to convert 12.5? 12 divided by 2. So it is 6, 0, then 2, 3, 0, then again 2, 1, 1. So it's 1, 1, 0, 0. Okay, 1, 1, 0, 0. And 0.5 is calculated by multiply 2. So it's 1. So 0.1. This is the binary. Now convert this binary number into the normalized floating point form. So what will we do? We will do 0.11 because it's lie between 0.1 and 1.0. So 0.11 into 2 raised to power 4. 1, 2, 3. Point goes this to becomes 2.4. So here Mantissa is 0.11001. Clear? So you understand how we do? Simply 0.11001 and 2 raised to power 4. Now Mantissa is extended to 23 bits. By simply adding 0 to the right, we get 23-bit Mantissa. So it is 11001 and 18 zeros we are adding here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 0 and 5 bits. These total is 23 bits Mantissa. Now convert exponent 4 to biased exponent. So by adding 128 and then convert to 8-bit binary. So biased exponent is 4-bit, 2 raised to power 4 plus 128, that is 132-bit. So 132-bit means 132 is binary. 2, 6 to the 12, 6 to the 12, 0. Again 2, 33, 0. Again 2, 1, 2, 6, 1. Then again divided 2, 8, 0. Then again 2, 4, 0. Then again 2 to 4, 0. Again with 2, 1, 0. So this is 1, 0, 0, 0, 0. 1, 0, 0, 4 times 0, 100. So this is 132-bit. The biased exponent in binary is 10,100. Okay. Step number 5, plus 12.5, the sign bit is Mantissa is 0, and for minus 12.5 sign bit will be 1. Now combine the binary form of biased exponent in 32-bit. So what is sign biased component? That is 132, means 132, that is 8-bit biased. For the plus it is 0 and 23-bit the Mantissa part. And similarly for minus 12.5, 8-bit means a biased exponent. 1 is for the negative sign and rest 23-bit is the Mantissa. In this way you can represent plus 12.5 and minus 12.5 in floating point representation in 32-bit format. I hope you understand and share my video. If you have any doubt, you can comment. You can write in comment section.